all the way through and eventually I find the right answer. If I wanted to go faster, I split the directory in two, and faster still, I just keep adding more computers to split the directory up. In the quantum computing world, we look at all possibilities at the same time. So to give you an idea of how this works, I'm going to show you two equations, and then we'll get into understanding the field. So imagine in the classical world, I'm a bit of information. I can either point at the North Pole or the South Pole. In the quantum world, I can point in between those two states. And mathematically, I write that down as some fraction, alpha 0 of the down state, and some fraction, alpha 1 of the up state. So a quantum bit, or a qubit, contains two classical bits of information. This is called superposition. If I take two qubits and I bring them close enough together, they entangle. So they form one unified state with all the individual components, 0, 0, 0, 1, 1, 0, and 1, 1. But now there are four classical bits of information in that same state. So what I've done is I've doubled the amount of classical information. But when I perform any kind of algorithm, I perform an operation on these states, and I do it on all the individual components at the same time. So I'm accessing massively parallel computing as I add my qubits. So every time I add a qubit, I essentially double the computational power. So by the time I get to a 50-qubit system, I'm more powerful than the world's most classical computer that exists. And if I get to 500 qubits, it's more powerful than all the computers in the world connected together. So that is the international race to build a quantum computer with 500 error-corrected qubits. To get access to the quantum world, I have to make things very small. And to make things small, I go down towards the atomic scale. The smaller it is, the higher the quality of the qubits, and the longer they last. And so this is Moore's law, Gordon Moore from the silicon industry, who shows that every year transistors get smaller and smaller and faster. And so in the quantum computing world, eventually you cross over to where quantum physics dominates. And if you get down to the smallest length scale of matter, you're down at the atoms, and that is where the highest quality qubits occur. So this orange picture is an image in our labs where we've individually placed atoms on silicon surfaces. Australia is a world leader in quantum computing. It got into the field back in 2000, so 25 years ago, and it set out with an ambition to build a silicon-based quantum computer based in Sydney. We have centres of excellence which have basically 250 people across the country working together to help build this processor. And over the last 25 years, we've produced many thousands and thousands of researchers with the aim of building a full-scale error-corrected system. In 2015, we set up the first quantum computing company. So Silicon Quantum Computing was launched in May 2017, and we're using individual phosphorus atoms in silicon as our qubits. They're very high quality. We call it the 1415 platform for elements 14 silicon and elements 15 of the periodic table. And we manufacture with 0.13 nanometers precision. That's the highest precision accuracy on the planet. So the smallest feature size with TSMC is about 5 nanometers. So we're an order of magnitude or two below that. We figured out how to manufacture the whole chip at that scale, so there are only two qubits, two atoms in our whole system, phosphorus and silicon. And we're already making products that are driving millions in revenue. Using this technology, we put atoms in place, and we made the world's first single atom transistor in 2012, and the first integrated circuit in 2022. We've also been able to manufacture in all three dimensions. So we are making the highest precision, highest quality qubits on the planet. And the interesting thing is that we do this in silicon, and we do it with a manufacturing speed of less than a week. And that compares to about 16 to 40 weeks with a kind of conventional foundry process. So if you want rapid learning cycles, rapid iteration, then ours is the fastest way to get that. The advantage of going to atom-based systems is you get very high quality qubits. You can see our fidelities now for single qubits are 99.99 and two qubits above 99.9%. But most importantly, we want to run algorithms. So how accurately can you run an algorithm? One of the key algorithms is what we call the Grover's database search algorithm. And we have the world record fidelity accuracy for that algorithm at the moment. And that really comes about from manufacturing these precision atom qubits in silicon. About 2 years ago, we got a new chair of our company with Simon Segars. He's the ex-CEO of ARM Computing. Everyone in this room will have ARM microprocessors running their chips inside their mobile phones. So he has taken a company from employee number 16 all the way through startup to scale up selling it for $24 billion a few years ago to SoftBank. So having that commercialization is quite critical because the quantum computing market, if you haven't already spotted it, is taking off. It's a $1 trillion industry predicted by 2050. We know that CPUs deliver the modern world. We know that GPUs are delivering the artificial intelligence, and QPUs, quantum processing units, are the next frontier of computing. And you can see it comes across every industry sector. So here we have some examples of where those algorithms are coming out in the AI space is the first area, in cryptography, in optimization, in understanding molecular structures and materials discovery. And you can see here, just taking that example of corrosion-resistant materials, it is an industry that's worth trillions of dollars. So if you can figure out how to stop corrosion either on ships or airplanes, it's a massive industry that needs huge compute power, which cannot be done classically. There are now over 85 different algorithms that are listed on a US government website. So this field has started off by having hardware developing, but also the algorithms developing at the same time. So there's huge application across multiple industry sectors. And very recently, DARPA, the US Defense Agency, identified these algorithms that they see as closest to the near-term value. And you can see a lot of those are in the areas of materials catalysis, so trying to figure out a better way to create fertilizers, looking at magnetic materials or high temperature superconductivity or rocket fuels. But also in there is cryptography. So the code-breaking algorithm is now predicted within the next 5 to 10 years. DARPA has had a program out for the last few years funding quantum computing companies across the globe. And so there are 16 companies that are now in this program. It's a very exciting program to be part of. And what you'll see is the industry is changing quite dramatically with their entry into the field. So companies are now starting to pair up. So you've got examples of Microsoft working with Atom Computing, Atlantic Computing working with Google AI, and IonQ has recently acquired Oxford Ionics. The interesting thing about these companies is that they will work alongside CPUs and GPUs. So quantum computing is not predicted to take over the field. It is predicted to be a hybrid process that works in synchronization with those other fields. One of the challenges in a new industry is there is a lot of hype. A lot of people are promising billions of qubits in a very short period of time, and that makes it hard for those people that are really building systems. A lot of them have to go through foundries. You'll see lots of pictures of chips coming out on these wafer scales. But in amongst the hype, there is real progress coming along, which is why DARPA, US Defense Agency, has started to come in to build full-scale systems. And so here are examples. There's our Grover's search algorithm result from very recently. You've got Quantinuum looking at 8-qubit processes, and you've got people looking at algorithms and recognizing those algorithms are now within reach by 2030 to 2033. So it's a very exciting time for the field. And if you can break the RSA encryption algorithm, that is massive for all defense industries. What you will see is the number of qubits increasing with time. And you'll see as you get more and more qubits, more and more of those algorithms of commercial value are coming closer to the window. And given that DARPA predicts this happening by 2033, you can be pretty sure that the acceleration that's occurring in the field is going to mean that's going to come before then. NVIDIA also has started to pay attention. So about 18 months ago, NVIDIA said quantum computing was too far away, at least a decade, and within a year they've changed their tune. So NVIDIA is now investing heavily in quantum computing companies, and you'll start to see the amount of earnings calls going towards those companies is increasing quite dramatically. One way to check how far a field is going is to look at the investment, but to also look at the announcements. So you'll see that Google very recently announced a 103 qubit system where they showed that they could get beyond break-even performance for their qubit processes. It's interesting for us because our quality is so high, we can do the same thing with just 3 qubits. Also, interestingly, last night, you would have heard that the Nobel Prize in Physics was won by the group of people, John Martinez, Michel Delray, and John Clark, for the superconducting qubits. So he was one of the founders of the Google team. You will see that Microsoft is talking about its Majorana qubits. Amazon is getting involved in multiple companies, and you're seeing public listings every day. The QBI program, like I said, has really changed things, but in amongst that, we're seeing lots of movement across the globe. But to understand why the field is taking off, we need to look a little bit under the hood and understand what the different platforms are. Unlike classical computing, where everything is made from silicon, in the quantum field there are many modalities, and I've split them into 3. In the light blue on the left-hand side is what I call the atoms and ions. These are the very high-quality qubit systems. But for them to operate, they're operating inside vacuums with lasers. So it's a technology that's never been demonstrated at scale before. The dark blue is where we look at the conventional top-down technologies. These are the industries like Intel, IBM, Google. They're using essentially foundry-based techniques to make their qubits. And typically their techniques are such that the physical systems are much bigger than the size of the qubit. So their manufacturing is way bigger than the actual qubit size. So they get a lot of off-resonance drive and errors. And at the bottom, you see the kind of optical qubit systems. These are the new kids on the block. They have to take optics, which works in free space, and integrate them on chip. And our company, Silicon Quantum Computing, is sitting at that nexus between atom-based systems, high-quality qubits, and a manufacturing material, silicon. So let's just look at those superconducting teams. They're typical US leaders in Google and IBM. They basically have micron-sized qubits, so they tend to find that their qubits don't last very long, but they are very fast. So they need a lot of qubits to error correct. If you look at ion trap systems, very, very high quality qubits, but they operated in a vacuum via laser and they're relatively slow. If you look at the optical systems, they're very fast qubits, but they have to create the qubit, transmit them in chip, and then detect them. And all of those things have not been demonstrated at scale. And then you've got the atom qubits. These are the systems that are the very fast, rapid growing systems. They're beautiful. They're in a vacuum. They work very well. They're moved around, but they actually move their qubits for the operations. So again, it's a system that's beautiful, but not demonstrated at scale. And then you end up with the silicon. I guess silicon has the advantage of being manufacturable at scale, but there's a lot of different modalities. And atoms and silicon are some of the highest quality systems that are out there. But you're more probably aware of Intel systems using the top-down techniques. And so the silicon ones, the atomic scale, are the ones I encourage you to watch. And then you look at Microsoft with the new state of matter, and that's fairly early on, and it's still unknown whether they have qubits working. So as I said, unlike classical, there are 5 different modalities of qubits globally, and there's a huge number of companies in each of those spaces. You can see the dollars invested are really going primarily to the hardware companies. So these are the companies that are building the actual hardware chips. And then there are lots of component companies that sit on top. But in amongst that, you can see in here that a lot of the raisings are going to those very large-scale hardware companies, primarily in the US at the moment. There you can see the hardware companies of the light blue region, and you can see that as time is growing, those hardware companies take the majority of the funding, and the software and the hardware components are above and below. So let's just look at some of the themes that are out there in the market. There are 6 themes that we see in the quantum computing world at the moment. One of them is sovereign investments. Every country wants to have its own play. So here you can see Pascal from France, Fujitsu from Japan, and obviously DARPA from the US. So there's big venture coming into those national programs. You're starting to see the rise of error correction, which is why I think DARPA's got into the field. So people are now showing that they can correct for errors in these qubits, and they can actually start to run algorithms that are getting more commercially viable. And that's typically in the small atom or ion-based systems. You're also starting to see other layers of the stack. So you've got people that come in with control electronics and control software and algorithm companies. So this is very different to classical computing, which is very vertically integrated. Quantum has seen it happen before and is starting to put companies at various layers of the stack. And then you start to see acquisitions. So IonQ has raised sufficient money that it's hoovering up all the connecting companies. So all the people working in quantum communications or other small atom-based companies, including Oxford Ionics. And now, for me, the most exciting part is you're starting to see quantum overlap with AI. And so we have a product in market now, which is actually using a quantum processor to enhance the accuracy of AI or to do time series prediction. That's something where classical machine learning, it's generating a lot of energy at the moment. There are people buying lots of large language models. But there are certain areas with sparse data sets and time series prediction where classical machine learning doesn't have enough data to learn from, and quantum systems can come in and basically increase the dimensionality of data to help in those spaces. I'll talk about that in a little while as we get towards the end of the talk. The other one is the return of SPACs. So these are special purpose acquisition companies that basically raise a lot of capital and they crowd in around these few modalities. So those are the 6 themes that are out there at the moment. It's really showing the transition of the field. And if we look at that, we know that the US started very heavily in quantum computing. It's one of the biggest investors, but now every country has got its own modalities. In Australia, it's largely described by silicon quantum computing at a company called Q-Control, which is a software control company. In the intellectual property, again, you see there's a lot of IP that's coming out of the Chinese region, but again, across the US and all the way down. And you can see Australia and Singapore listed in there in the blue lines. But taken together, the impact is really coming from the United States, Europe, China, and then countries like Singapore, Japan, to the Netherlands and Australia. One of the things that's changing a lot is you'll see now in universities that have degrees in quantum, so that's training the workforce as it comes through. And that helps us to build these companies. So in the last few slides, I'm just going to describe what our company does. If you have a high quality qubit, but you have something that's never been manufactured at scale, then you've got to keep figuring out how you manufacture as you increase qubit count. If you have low quality qubits and you try and scale them, you need more qubits around to correct for them, and you end up in this death spiral. But if you have high quality qubits and you control the manufacturing, then your quality just increases and the number of algorithms increases with time. And that's really the roadmap that we're following. We position atoms in silicon with atomic precision, and this technology is using a scanning probe system where we literally mimic the semiconductor process of opening up a resist of hydrogen on silicon to expose the silicon surface. We bring in our phosphorus atom, phosphine gas, which sticks at the silicon surface, and then we grow over it. And we can make 65,000 of these qubits in a very short period of time, in a few hours. We've developed the tools that manufacture these, and we're automating those tools now. And if you look at our manufacturing, it's completely unique. It's 0.13 nanometers precision. It's all done in-house. It's much less expensive than a conventional foundry process, which has a long turnaround time and has lots of overheads. But most excitingly of all, by controlling that manufacturing with that precision to get the high quality, we brought out our products. Our first product is Watermelon in the AI space. As I mentioned, it gives an increase in the accuracy of machine learning. We have quantum twins, so we can actually replicate molecules exactly by putting the atoms the same distance apart as the materials we're trying to simulate. And then we've got our error-corrected processes, which allow us to get to those big algorithms that I described at the beginning. So let's just take a minute or so to talk about Watermelon. How does that work? In the classical world of AI, you take quantum features, you normally pass them through some kind of random neural net, increase the dimensionality, and then you use that high dimensionality data to train your AI. And this is an example of taking two-dimensional data, the blue circles and the dark blue, light blue and dark blue circles. To try and differentiate between those in the line is very difficult, but if I transfer that to 3 dimensions on the right-hand side, I can draw a plane between them. So going to higher dimensionality allows you to identify features in a way that you cannot do very easily without that. And what a quantum processor does is it takes it and it exponentially expands the dimensionality of the data, so it gives you a lot more data to learn from. That's showing that we can do time series prediction, we can look at control systems to modify it, we can do anomaly detection, and we can do classification in a completely different way from classical AI. We have customers that have been testing it for the last few years, and you'll see that emerging in the next few weeks because we're going to be announcing it next week. So if you're a global company and you're watching the AI space take off, you know that quantum is the next compute frontier. What do? The key thing to do is to get involved with those quantum hardware companies that have products in market today, work closely with them, test them in the AI space, and you can see how well they work, and then build through as they get bigger and bigger error-corrected processes until eventually you will incorporate quantum systems into your conventional compute world. So with that, I'd like to thank you for your attention. I have 1 whole minute left. In our company, every atom counts. Thank you.